All right, so we're in section 2-3 of the differential equation book, and we're going to have some differential equation. It doesn't necessarily have to be second order. It could be third order or fourth order or first order, and these methods still work. It's going to have a characteristic equation. That characteristic equation is going to be something where we keep the constants and replace the derivative guys with r's. We could also do it with m's. I've seen it that way too. And then we have an equation that can have roots. So if the roots of the equation turn out to be distinct roots, r1 and r2, then the solution, the general solution to our differential equation will be y of x is c1 e to the r1x plus c2 e to the r2x. And as long as r1 and r2 are distinct, then e to the r1x and e to the r2x are going to be linearly independent, and then I have two linearly independent solutions. I can solve for c1 and c2 if I have initial conditions. If I don't have initial conditions, then I can't. The other possibilities is that I could have the same root, r and r, in which case my answer would be c1 e to the rx plus c2 x e to the rx. Now, the e to the rx and x e to the rx are linearly independent things, and I have two separate solutions that are linearly independent. And in order to solve for c1, c2, I need initial conditions. So I have an infinite number of solutions for my general solution. Once I have initial conditions, then I have a solution. If you recall, you probably don't, but e to the ix is equal to cosine x plus I sine x. Do you recall that from anywhere? You don't? Okay, well, in your complex variable class, you'll get to that. So if my roots are in the form alpha plus or minus beta I, then that's where I'm getting this cosine x sine x from. Clearly, cosine x and sine x are linearly independent to begin with, but if I throw in an I in front of the sine x, then it still is more linearly independent because now I'm an imaginary number. So, that's being the case, then my answer, y of x, becomes e to the alpha x c1 cosine x cosine beta x. That's a beta. It's not a b. Plus c2 sine beta x. Does it matter if it's a beta or a b? No, doesn't. Okay. So those are the things that we're going to be dealing with, and I could have something extremely complicated that would have more than that. So I could have something that, so let's say that I found out that I had roots that were 1, 1, 1, alpha plus or minus beta I, alpha plus or minus beta I. So I got repeated roots that are both real and imaginary. Then my y of x would be c1 e to the x plus c2x e to the x plus c2x squared e to the x plus e to the alpha x c3 cosine x plus c4 sine x plus x e to the alpha x, and there's a beta there, and there's a beta here, c5 cosine beta x plus c6 sine beta x. And now I have something that's worthy of your complication, right? instead of something that is just marginally complicated. So I could have that too. So I could have a higher order characteristic equation giving me multiple roots, and that'd be perfectly okay too.
How come you have two C2s then?
Probably because this needs to be a 3, and that needs to be a 4, and that needs to be a 5, that needs to be a 6, that needs to be a 7.
Okay.
Yeah, exactly. Okay, so we'll look at problems going to 49. So we'll solve problems until 4 o'clock and then switch to the next chapter. So we'll look at 8 first, just to have some place to start. So I've got y double prime minus y 6y prime plus 13 is equal to 0. And I have a characteristic equation. R squared minus 6r plus 13 is 0. I see that I can't factor that, so I'm going to use the half quadratic formula that I used last time and call that 3 plus or minus the square root of 9 minus 13 divided by 1. And so that's a 4, so I'm going to have 3 plus or minus 2i as my roots. And I find that my final answer would be C1, e to the 3x, C1 cosine 2x plus C2 sine 2x. And then if I wanted to, I could check that, and I could say, well, y prime would be 3e to the 3x c1 cosine 2x plus, well, then I'd have, I could do that if I wanted to, but this is pretty simple, so I'm not gonna. I'm gonna look at number 10 next. So I got 5y fourth derivative plus 3y third derivative equals 0. So I've got a characteristic equation which is going to be 5r to the fourth plus 3r cubed, and I can factor that r cubed 5r plus 3, and I find that I have r's that are going to be 0 and 0 and 0, so I have 3 roots of 0, and then I've got minus 5 over 3. No, I don't. I have minus 3 over 5. Okay, so my final answer would be y of x is equal to c1 plus c2x plus c3x squared plus e to the minus 3/5 x. And then it's not so obvious that that's the right answer, so we will check our work. Y is c1 plus c2x plus c3x squared e to the minus c4. c4 e to the minus 3/5 x. There should be a c4 sitting there. Y prime c2 plus 2c3 x minus 3/5 c4 e to the minus 3/5 x. Y double prime 2c3 plus 9 over 25 c4 e to the minus 3/5 x. Y triple prime, that guy goes away, minus 27 over 125 e to the minus 3/5 x. Y fourth derivative 81, is it 625? 625 e to the minus 3 over 5x. I think that's what it is. Now I'm supposed to have 5 of those guys and 3 of these guys, and when I get done I should have 0 is what I'm supposed to have. And I see that 3 times 27 is 81, and 5 goes into 625 125 times. Those guys will go away. 0 is equal to 0, check. Okay, we'll move on to 14, 16. We'll move on to 16. Number 16, y fourth derivative plus 18y double prime plus 81y is 0. I have a characteristic equation. My characteristic equation is r to the fourth, 18r squared, 81 is equal to 0. I can factor that. R plus 9, r squared plus 9, r squared plus 9. And I can, from that, know that my r's are going to be minus 3, minus 3, 3, and 3. So I have double roots of minus 3 and 3 each. And that's not true. No. R to the 0 is 1. Yeah, so it's r to the fourth, r squared, r to the 0. There's no derivative there. But they are i's. So minus 3i minus 3i minus 3i. Alright, so I've got my roots are plus or minus 3i plus or minus 3i. Those are my roots. Alright, so final answer y of x is c1 cosine 3x plus c2 sine 3x, that's a 3, plus xc3 cosine 3x plus xc4 sine 3x. And again, I should probably check that, but I'm not gonna. Okay, moving on to 18. I have y fourth derivative minus 16y is equal to 0. So I got r to the fourth minus 16 is 0. So I got r squared minus 4 times r squared plus 4. And so I've got plus or minus 2, and I got plus or minus 2i on my roots. So y of x, c1 e to the minus 2x plus c2 e to the plus 2x plus c3 cosine 2x plus c4 sine 2x. And that would be my final answer. And I'd probably want to check my work on that. Okay, back to number 22. Uh, 9y double prime, 6y prime, 4y is 0, and I have some initial conditions. Y at 0 is 3, y prime at 0. Why do we always pick 0? Is 4. Well, normally we think of it as time. At time 0 something happens, and so, but we didn't have to necessarily pick 0. We just did, you know. Now in chapter 4, when we're doing Laplace transforms, we have to know the initial conditions at 0 in order for them to work. So that makes it convenient. Okay. Characteristic equation. 9r squared plus 6r plus 4 is 0. And can I factor that? I don't see that it's factoring. Do you see that it's factoring? I don't see that that's factoring. All right, I'm using the half quadratic formula, so I'm going to use 3 plus or minus the square root of 9 minus 36 over 9. So r is going to be 1/3 plus or minus 9 minus 36 is 27? Really? Yeah, so I got 3 square root of 3 over 3 over 9. 3 square root of 3 over 9. So r is going to be 1/3 plus or minus the cube root of 3 over 3. Right? And my answer is going to be, I still have initial conditions to apply. E to the 1/3 x c1 cosine square root of 3 over 3 x plus c2 sine square root of 3 over 3x. Okay, now I'm going to apply an initial condition and say y at 0 is 3. Okay, so this becomes a 1, that becomes a 1, I get a C1, that becomes a 0. So that implies very strongly that C1 is 3. So my equation becomes y of x e to the 1/3 x 3 cosine the square root of 3 over 3x plus C2 sine the square root of 3 over 3x. Okay, now I've got to look for y prime. Okay, so y prime is going to be 1/3 e to the 1/3 x times 3 cosine the square root of 3 over 3x minus what? The square root of 3 e to the 1/3 x sine square root of 3 over 3x plus 1/3 e to the 1/3 x sine square root of 3 over 3x plus square root of 3 over 3e to the 1/3 x cosine square root of 3 over 3x. Okay, now as long as I didn't space that off too badly, I can say y prime at 0 is supposed to be 4. Okay, this guy is 0, that guy's 1, this guy's 1, I've got a 1. I've got a minus 0, I got a plus 0 for those two guys. In this guy, I've got a plus square root of 3 over 3. So C, where's my C? Okay, here's a C2 I didn't write down. Here's my C2 sitting there. Here's my C2 sitting there. So I've got a C2 sitting here. So I have C2 is equal to 3 minus, 3, 9. Okay, so that makes it a 3. Alright, so I've got 3 times 3 divided by the square root of 3. Right, I invert that. And then I multiply top and bottom by the square root of 3, so I get that guy out of there. So now I've got 3 the square root of 3. So final answer, y of x equals e to the 1/3 x, 3 cosine the square root of 3 over 3, square root of 3 over 3x plus 3 the square root of 3 sine square root of 3 over 3x. Anybody not believe that? Should I check it? Or are we going to say it's okay? Well, the back of the book gives answers to these guys, right? That was number 22. I'm pretty sure it gives the answer to the even guys. Okay, I'm in chapter 2.4. 2.4, number 22. 2.3. That would make a difference. 2.3, number 22. E to the minus. Where did my minus sign go to? 3 cosine plus 5 square root of 3. Oh, bummer. Alright. All the way to the top. That's a positive number, and we have to have a negative there. And if we have a negative there, we have to have a negative here, we have to have a negative there, we have to have a negative here. And the 3 is still correct, even though that has to be negative, that has to be negative, this has to be negative, that 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 has to be negative, and minus, minus, that has to be positive. Okay, so now I'm going to have minus 1, 0, 0, and I'm going to have square root of 3 over 3 C2. That's going to be a 5, 5, so that's going to be 15 divided by the square root of 3. So that's going to be 5 the square root of 3 when I get done. Yeah, 5 the square root of 3 when I get done, because this is going to be a 5, and this is going to be 5 the square root of 3 with that being a minus sign. Okay, certainly glad we did that. Okay, we'll do 26. Y third derivative. 10y, 25y prime equals 0. Y at 0, 3, y prime at 0, 4, y double prime at 0, 5. Somebody must have been really hard-pressed to get those initial conditions right. Okay, well, I have a characteristic equation. R cubed 10r squared 25r is 0. I have r. I have r plus 5. R plus 5 is 0. So I have my r's are going to be 0, minus 5, and minus 5. My answer, y of x, is going to be C1. When I go e to the 0x, that becomes a 1, so I don't have to write it down. plus c2e to the minus 5x plus c3ex, e to minus 5x. I'm applying my initial conditions. Y at 0 is 3, which is c1 plus c2. That guy goes away. Y prime of x is minus 5c2 e to the minus 5x plus c3 e to the minus 5x minus 5 c3x e to the minus 5x. Y prime at 0 is 4, which is going to be minus 5c2 plus c3. Okay. Y double prime x. 25 e c2 e to the minus 5x. I have minus 5. I have another minus 5 for a minus 10 c3 e to the minus 5x. And then I've got a plus 25 c3x e to the minus 5x. And y double prime at 0 is 5, which is going to be 25c2 minus 10c3. I'm going to go and open up my simultaneous equation solver in Excel, and just in case I need it. There we go. Simultaneous equation solver in Excel. Did I put that on the spreadsheet for you? I don't know if I put that on the course for you, but I have it just in case I need it. Okay, so my first thing I know is C1 plus C2 is 3. C1 plus C2 is 3. And then I know that minus 5 C2 minus 5 C2 plus C3 is 4. And then I know that 25 C2 minus 10 C3 is 5. So those are the things that I know. I'm going to use Kramer's rule on it real quick before I put in the Excel spreadsheet thing. C1 equals 3, 4, 5, 1, minus 5, 25, 0, 1, minus 10. And I have 1, 1, 0. I have 0, minus 5, 1, 0, 25, minus 10. Okay, so that guy is, we'll do the bottom pair first. 50, 0, 0, 0, minus 25, 0. Okay, so on the bottom I got a 25. On the top I have 150 plus 5 plus 0 minus 0, 75, and minus 40. So it looks like C1 is going to be something over 25. So I got 150 minus, is that 35? Minus 35. I have 155. 155 minus 35, 120 divided by 25, 4.8. So C1 is going to be 4.8. Do we believe that? All right. C1's 4.8. Okay, so I got 1, 1, 0. I have 0, minus 5, 1. 0, minus 5, 1. I've got 0, 25, minus 10. And that doesn't look like what I said it was. 1, 1, 0, minus 5, 1. Oh, over here I need a 3, 4, and a 5, right? Oh, 4.8. Lucky guess, right? Is that what I got? 4.8? So C1 is 4.8, which I already calculated. And then C2 and C3 are to come. And minus 1.8 minus 5, minus 1.8 minus 5. So my final answer, y of x, is equal to 4.8. And that's just a constant, right? Yeah, 4.8 plus, or is it minus? Minus 1.8 e to the minus 5x minus 5x e to the minus 5x. And at that point, we'd have to go and check our work. Should we do that, or should we just say that? Oh, we just look in the back. Except it takes a long time to do that because I always lose my place in the back of the book. So this is 23, section 23, number 26. Right. Well, that's not what the book says, is it? Yeah, 26. So the book wants us to have something different. And it wants us to have, no, 24 divided by 5 is what? Well, stupid computer. 24 divided by 5. Yeah, that's 4.8. So it wants 4.8 minus 9 goes into 5. Okay, that's 1.8. Yep, same answer. Same. So they brought out a 1, they brought out a fraction, whatever it was. 1/10? Yeah, they brought out a 1/5. Bunch of overachievers anyway. Don't they know when to quit? Now if I go and I take my book and I put this paper clip on the page I want to go to, I bet you I can find it quicker. What do you think? Okay. Let's move down to 32. And how deep are we supposed to go? We're supposed to go to 49. So we'll look at 32. Y fourth derivative, y third derivative, 3y double prime, 5y prime minus 2y is 0. And we look at that and we say, I'm glad I remember my algebra 1. Okay, so characteristic equation, r to the fourth plus r cubed minus 3r squared minus 5r minus 2 is 0. And I look at that and say, minus 1 appears to be a root. Is minus 1 a root? Yeah, minus 1's a root. Minus 1 plus 1, they go away. Minus 1, 5, minus 5, they go away. So r equals minus 1 is a root. So r plus 1 is the factor. Now, if we had done synthetic division more recently than I had, I would use synthetic division to do this. But seeing that I didn't, I'm not going to try because that's a skill that one gets by using it. Okay, so that goes into there, r cubed times r to the 4th r cubed minus 3r squared minus 5r. That goes in there, minus 3r times minus 3r squared minus 3r minus 2r minus 2. That goes in there, minus 2r times. Something's wrong. How can that be? Okay, there's no r squared term. Okay, then I see that's just a 2 minus 2, no r. And this is r cubed. Okay, so now I've got r cubed minus 3r minus 2. And I see that r equals minus 1 works. So r plus 1 is a root. So r plus 1 going into r cubed minus 3r minus 2. R squared. R cubed plus r squared minus r squared 3r minus 2 minus r squared minus r minus 2r minus 2 minus 2, and I see that r minus 2, r plus 1 are my factors. So my roots become minus 1, minus 1, minus 1, and 2. Minus 1, minus 1, minus 1. Minus 1, minus 1, minus 1, and 2. So my final answer is y to the x is equal to c1 e to the minus x plus c2x e to the minus x plus c3x squared e to the minus x plus c4 e to the 2x. And that's all I have for my answer, and that's number 32 and 32 checks. Okay, excellent. Checks, back of book. All right, I think we're going to go to section 2-5 next. Well, no, we don't want to do that. There's a hyperbolic cosine one to solve. See, isn't there? Well, look at 41. And problem, find a linear homogeneous constant coefficient equation with the given general solution. Yeah, we'll do that. We'll do number 41. We normally don't do the even ones, but we'll do this one because it has a thing in there. So I have my answer. My answer is a cosine 2x plus b sine 2x plus c hyperbolic cosine 2x plus d hyperbolic sine 2x. Now, we remember that the hyperbolic cosine of x is e to the x plus e to the minus x over 2. And that the hyperbolic sine of x is e to the x minus e to the minus x divided by 2. So we remember that. That being the case, my roots of my characteristic equation had to be plus or minus 2I in order to get the sine and cosine, and had to be plus or minus 1 in order to get the hyperbolic, plus or minus 2 to get the hyperbolic cosine and hyperbolic sine. So those are my roots. So that means that my equation would have had to look like y, it had to look like r plus 2, r minus 2, r plus 2i, r minus 2i. And then we'd want to multiply that out. Okay. And of course we want to do that in maple so we didn't mess it up. I'm thinking I can do that on this calculator, can't I? Maybe not. But I can do it in maple. Okay, so I'll do that. So I've got x plus 2 times x minus 2 times, and we really want to do it with r's, don't we? R times r plus 2i times r minus 2, and we're probably going to have to put a multiply sign there while we're at it. I probably should put one back here too. Thank you very much. You're just so helpful. I mean, I'm just so happy that I paid all this money for you. Piece of crap machine. Expand, right? E-X-P-A-N-D. Oh, way to go. If you put a colon, that means it suppresses your answer. Oh, r to the 4th minus 16. Okay, now that we know it's r to the 4th minus 16, and we should have been able to get that, right? That was the case. R to the 4th minus 16. So our differential equation would be the 4th, r to the y to the 4th derivative minus 16 is 0. So that would have been the equation that would have given you that solution. See how that works? So we just worked the problem backwards. And it's and of course we got the wrong answer naturally with 16y. All right, that's better. Okay, good enough? Moving on to section 25, way to go. Just totally wonderful. 2-5. So in 2-5, what we do is we end up having a forcing function. So we have something y double prime plus y prime plus y is equal some forcing function what we do is we find the characteristic equation of the homogeneous problem. So of y double prime plus y prime plus y is equal to 0. We find that characteristic equation and we solve for it. So we get the homogeneous solution, and then we go back and we look at a particular solution, y sub p. Y sub p is going to be the forcing function plus the derivatives of all the forcing function until I run out of them. And each of them are going to have a constant in front of it. So I'm going to have f of x plus b f prime of x plus blah, 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 blah. And then I'm going to solve for this a, b, and c. And when I do, I will have y sub p, my particular solution. And then my final answer is going to be the homogeneous solution. If I could write the homogeneous solution. The homogeneous solution plus the particular solution that I just solved for. Okay, so whatever I did in the last section, I get it to do it over again twice. Okay, so that's the plan. And there's nothing weird about it until, and there's still nothing weird about it, until we get to page 157. And page 157, we now turn weird. And we say, well, what happens if I have some forcing function like tangent x, and now I can't find all of its derivatives? What am I going to do now? Okay, well, what I'm going to do now is use something called variation of parameters. And on page 158, 159, it tells you how. But on page 168, it says that if you have something in the form y double prime plus p of x, y prime plus q of x, y double prime is equal to some forcing function. If you have something that looks like that, and you can find the homogeneous solution y of c, c1y1x, c2 y2x. So you can do that, and you have that answer, and you know what y1 and y2 are. Then your y sub p can be calculated directly as minus y1x integral y2x, the forcing function, divided by the Wronskian of y1, y2, plus y2x, the integral y1x, the forcing function of x, divided by the Wronskian of y1, y2. And both of those are dx's, dx, dx. Now, never do this. You have to do this on the next test. There's going to be a variational parameter question on the next test. When you're doing it, make sure your book is open to page 160 and you're doing exactly what it says to do. Make sure that when you have your y1 and y2, so I find that I get my characteristic equation, r is going to be minus 1 and 1. Then put them in that order, numerical order, ascending order, just like that. y1 is e to the minus x. y2 is equal to e to the x. If you do it the other way around, you're going to get the wrong answer. Okay, so if you said y1 is e to the x and executed this formula, you'd be wrong. If you said y2 is e to the minus x, you'd be wrong. So put them in ascending order, have them in ascending order, make sure you're on that page, and solve the problem. And that's an alternative way to finding the y sub p. And it's done directly. There's no constants of integration involved. What you have is the answer, and you'd add it to the y sub c solution that you already have. So just because you got it doesn't mean you have your final answer. You still have to add it to the solution to the homogeneous problem in order to have the right answer. Okay, now that we wanted to know all that, we're going to look at number 2. And we have y double prime minus y prime minus 2y is 2x plus 4. And we find a characteristic equation associated with the homogeneous solution. R squared minus r minus 2 is 0. We can factor that r minus 2, r plus 1 is equal to 0. We see that our r's are minus 1 and 2. We see that the solution to the homogeneous equation C1 e to the minus x plus C2 e to the x. We have some particular solution y sub p, and I have something with an x in it, so I'm going to have, that means I have a constant a and I have a bx. So that is the forcing function and all of its possible derivatives is represented by that.
Isn't for the characteristic equation, are you supposed to have one of those like C2E 2x?
Oh yes, like that one there?
Yeah.
Yeah, okay. And I'm going to take the first derivative of the particular solution and get a b, and I'm going to take the second derivative and I'm going to get a 0. And then I'm going to say, when I solve this differential equation, I want a 3x plus 4. That's what I'm looking for. And so if I have one of them, and I have minus 1 of this guy, and I got minus 2 of that guy, then I must have minus 2a minus 2bx minus b has to be 3x plus 4. So I look at the x term, and I see that minus 2b has to be 3, implying that b has to be minus 3 over 2. I look at the unit term, and I see that minus 2a minus b has to be 4. And I see that I already know what b is, so I can put that in. Minus 2a plus 3 over 2 is equal to 4. Minus 2a is equal to 5 over 2. A is equal to minus 5 over 2. Minus 5 over 4, minus 5 over 4. Okay, so now my y sub p becomes minus 5 over 4 minus 3 over 2x. So I put the a and b back into the original equation, wherever that was. So the a is there, plus bx, so I've got that guy. Now I got my final answer. Final answer. Y of x, c1 e to the minus x plus c2 e to the 2x minus 5 over 4 minus 3 over 2x. And then I would check my work to make sure it was right. And this is section 5.2.5 and 2.5 number 2. And all they wanted was the particular solution. Doesn't that just mess you right up? And our particular solution is correct. So if you would have read the problem, it said, find the particular solution. Okay. So I found more than the particular solution, but at least I found a particular solution. We look at 8. Now I'm going to find the particular solution. So y sub p is going to be in the form a hyperbolic cosine 2x plus b hyperbolic sine 2x. Okay, and y prime of p is going to be 2a hyperbolic sine plus 2b hyperbolic cosine, and y double prime is going to be 4a hyperbolic sine plus 4b hyperbolic cosine. Okay, so the derivative of cosine, hyperbolic cosine is hyperbolic sine, the derivative of hyperbolic sine is hyperbolic cosine, and whatever's in front of the x has to be taken care of too. Okay, so I've got 4 of those minus 4 of those, and when I get done, I'm supposed to have hyperbolic cosine 2x. Okay, so I got minus 4a plus 16a hyperbolic cosine 2x minus 4b plus 16b hyperbolic sine 2x. From that, I will conclude that b is 0, because that coefficient has to be 0, and this guy has to be 1. So 12a is equal to 1, implying that a is equal to 1/12. So y sub p is equal to 1/12 hyperbolic cosine 2x. And that's problem number 8. And I'm wrong. Why am I so wrong?
They're negative when you change the sign hyperbolic.
No.
Okay.
That's not the issue. Oh, the authors stuck me in the back. Okay, I'm finding the particular solution. So I'm ignoring the homogeneous equation. Wrong. If the homogeneous equation includes the forcing function, then I'm forced to do something else. Okay, so now I got to go back to number 8 and say, well, r squared minus 4 is equal to 0. R squared, r is going to be plus or minus 2, right? And one could say, well, r is plus or minus 2, so that's e to the minus 2x, e to the 2x, right? But that's the same as saying that those are hyperbolic cosines or hyperbolic sines. So the hyperbolic cosine has those solutions in it. So that means my y sub p is going to be in the form a hyperbolic cosine 2x plus b hyperbolic sine 2x plus cx hyperbolic cosine 2x plus dx hyperbolic sine 2x. And that is what I need to solve to see what my A, B, C, or D is. Okay, well, that's a horse of a different color. Y prime P. Okay, so I got 2A hyperbolic cosine. I got 2B, that's 2A hyperbolic sine, 2B hyperbolic cosine, C hyperbolic cosine, 2CX hyperbolic sine, D hyperbolic sine, 2dx hyperbolic cosine. Oh, I hope I did that right. And then I got y double prime, and I've got 4a hyperbolic cosine, 4b hyperbolic sine, I've got 2c hyperbolic sine, I've got 2c hyperbolic sine, I have 4cx hyperbolic cosine, I've got 2d hyperbolic cosine, I've got 2d hyperbolic cosine, and I've got 4dx hyperbolic sine. Isn't that just lovely? Isn't that just lovely? I want 1 minus 4, so I want minus 4 of them. I want 1 of this guy. And even though I can't see the whole equation, when I get done, I have to have hyperbolic cosine 2x. Okay, so that should be pretty easy. So I got minus 4a, I got plus 4a, gonzo, gonzo. I got minus 4b hyperbolic sine, I got plus 4b hyperbolic sine, they go away. I got minus 4cx hyperbolic sine, minus 4c, minus, where is it? Minus 4 dx hyperbolic sine, minus 4 cx hyperbolic cosine. Okay, and then what I've got left over is 4c hyperbolic sine and 4d hyperbolic cosine, implying that c is 0 and d is 1/4. Now what can I conclude about a and b? I don't need them. They went away. That's what I can conclude. So my y sub p becomes 1/4 whatever the d term was. So the d term was x hyperbolic sine, x hyperbolic sine 2x. Okay, thank you, author, for reminding me of that. Okay, we're going to do number 20. You like that one? Was that cool?
How did you go to start that one?
Oh, I've been doing it since 03. Yeah. So how did I know to go back and look at the characteristic equation to see that I had to go and add an antiderivative to my starting point in order to get the right answer? Well, if I didn't do that, if I didn't have these guys in there, what would have happened is that those guys would have canceled out and I would have had nothing. And that would have keyed me in. Because if I had done it with just hyperbolic sine and hyperbolic cosine by themselves, they would have canceled out. I wouldn't have had anything. Is that not what I did first? So the first time I did it, no, I ended up with B was that. Okay, so obviously I am hosed somehow. Oh, this is a 1. That's my problem. See, with that being a 1, then that and that would have canceled, this and this would have canceled, and this would have been 0, and I didn't get what I want. So that would have keyed me into, I have to add an antiderivative, it's something x guy, in order to get the right answer. So normally I have the forcing function and all its derivatives, but if the forcing functions, if the roots of the characteristic equation are part of the forcing function, then I have to add an antiderivative into that mix. So I have to throw an x in. Yeah. Did I wave my hands enough? How do I know to do it? How do I know to work the problem right? Yeah, I know. Is that great? Yeah, I think that, yeah, I agree. What you need to do is teach the class for about 5 years and you'll be just fine. Don't worry about it. Number 20. The third derivative minus y e to the x plus 7. Okay, we're not going to fall in the same trap again. So I got r squared minus r cubed minus 1, right, is 0, is the characteristic. So that's r minus 1 times r squared plus r plus 1. Is that what it is, or is it 2r? 2r plus 1 maybe? Whatever it is, r is equal to 1 is a factor of that. And because of that, when we look at the forcing function, is r is 1. And the other two are imaginary, right? So y sub p is going to be a, because of the constant, going to be b e to the x, but it's also going to be c x e to the x because I have that minus 1. I have that r is equal to 1 sitting there in my formula. Okay, so y p prime b e to the x c e to the x cx e to the x y double prime b e to the x 2c e to the x cx e to the x. And this is a triple prime guy, right? Triple prime b e to the x 3c e to the x cx e to the x. Okay, and I want 1 of that guy minus 1 of this guy, and when I get done I want to have e to the x plus 7. That's what I want. Okay, so I got a minus a, I got a minus b to the e to the x, a plus b e to the x. I got a plus 3c e to the x plus, oh, I don't believe, oh yeah, I did that. Okay, so minus c, okay, those two guys go away. Alright, so that's all I've got. Okay, so a is equal to minus 7. So that minus 7 is a plus 7. And 3c has to be 1. So c is equal to 1 over 3. So final answer, y sub p is minus 7 plus 1/3 x e to the x. And this is problem number 20. And minus 7 plus 1/3 x e to the x. So checks with back of book. All right, looking at 22, you gotta be kidding me. In problems 21, set up the appropriate form of y sub p, but don't bother to calculate it. Okay, that was a good one. I like that. Okay, so we're just going to set up the appropriate form. 22. Y, the fifth derivative, minus y, the third derivative, e to the x, 2x squared minus 5. Okay, so my characteristic equation, r, going to have roots. Going to be r. Oh, well, we'll just write it down. R to the fifth minus r cubed is 0. So I'm going to have r cubed, r squared minus 1. And that's going to factor r cubed, r plus 1, r minus 1. So I have 0, 0, 0, plus or minus 1. Okay, so this is a unit, an x squared. I already have an x squared, plus or minus 1. Okay, so plus or minus 1 is that e to the x guy. So y sub p is going to be a plus bx plus cx squared, and because x squared is in there already, I'm going to have to add a dx cubed plus e to the minus x plus f e to the x plus g x e to the x. Oh, well, that was okay. Number 22. And it doesn't have the e. Oh, I don't need an e to the minus x. Yeah, there's no e to the minus x over here, so I don't need an e to the minus x. So I can get rid of that guy. So I can write it all in one line. E, A, B, C, D, E to the x, f, x, e to the x. All right. Very good. We'll do 30 the same way. Number 30. Y, the fourth, minus 2y double prime, plus y, x squared e to the cosine x. There's no e there. Get rid of the e. Okay, so this guy's got a characteristic equation r4 minus 2r squared plus 1, and that's going to factor r plus 1, r minus 1, right? No, it's not. It's not going to factor that at all. It's going to be that, like that. And then I'm going to have r plus or minus 1, r plus or minus 1. So r is going to have roots plus or minus 1, plus or minus 1. All right, we can get rid of that line. And none of those guys are up here, so they're not going to deal with me any problems at all with my guy. Okay, so y sub p is going to be a cosine x plus b sine x plus c x cosine x plus c dx sine x plus e x squared cosine x plus e x squared sine x. Okay, all done with that. Solve the problem. So we finally get to a problem where we get to solve something. Number 32. Y double prime 3y prime 2y e to the x. Y at 0, is 1, y prime at 0 is 0. Right. I have a characteristic equation of the homogeneous equation. R squared plus 3r is equal to, plus 2 is equal to 0. That factors r plus 1, r plus 2. R is equal to, solution set, minus 1 minus 2. Y sub c is going to be c1 e to the minus 2x plus c2 e to the minus x. Notice that I put those in alphabetical order. Y sub p is going to be a e to the x. Yes, it is. And y sub p prime is going to be a e to the x. And y double prime of p is going to be a e to the x. Right. When I add up the appropriate number of those things, I want e to the x. All right, so I've got 1 of them, 3 of them, 2 of them. So 2, so I got 6a e to the x, implying that a is 1 over 6. So y sub p is 1 over 6 e to the x. Writing down the final answer. Final answer, y sub x, no, not final answer, because I still have initial conditions. Darn. Alright, so y sub x is equal to the homogeneous solution plus the particular solution. And I wrote that down because I forgot what it was. C1 e to the minus 2x plus C2 e to the minus x plus 1/6 e to the x. So that's my final solution, but I have to solve for initial conditions. Okay, so y at 0 is 0. Is that what I put down, really? And so that's going to be C1 plus C2 plus 1/6. Okay, y prime of x minus C2, C1 e to the minus 2x, minus C2 e to the minus x, plus 1/6 e to the x, and y prime at 0 is 3, which is minus 2c1 minus c2 plus 1/6. Right, so I have simultaneous equations to solve, and they are c1 plus c2 is equal to minus 1/6, and minus 2c1 minus c2 is equal to 17 over 6. Okay, so I did that right. That's not going to help in my spreadsheet because I can't put a 1/6 in easily. I probably could. Anyway, Kramer's rule. C1 is minus 1/6, 17/6, 1 minus 1, divided by 1, 1, minus 2, minus 1. Okay, so I got minus 1, minus a minus 2, so I got a 1 on the bottom. I got a minus a 6, I got 1/6, minus 17/6, which would be 16/6, which would be 8/3. 8/3. So if C1 were 8/3, then C2 would have to be minus 17/3. Really? C2 would have to be minus 17/3. Highly unlikely, right? No, I'm looking at the wrong thing. C1 is 16 thirds, right? 16 thirds. Then I'd have to minus 17 thirds. C2 would have to be minus 17 6, right? But how does that reconcile? Okay, so 2 times 8 thirds, no, clear, minus 2 times 8 thirds plus 17 6 equals minus 5 halves. That ain't right. Now, what am I doing wrong? 1/6 minus, this is minus, this is minus. Okay, so if it's minus 8 thirds, okay, so I got minus 8 thirds, so C2 would have to be minus 1/6 plus 8 thirds, which would be positive 5 halves. Okay, so minus 8 thirds plus 5 halves equals minus 1/6 minus 2 times minus 8 thirds minus 5 halves equals 16 6. Okay, so that's right. So now I'm ready for my final answer, I think. Am I? No, I haven't found y sub p. Have I found y sub p? Yeah, I found y sub p. All right, so now my final answer. Final answer. Y of x equals minus 8 thirds e to the minus 2x plus 5 halves e to the minus x plus 1/6 plus 1/6 e to the x. And the author probably, when it multiplied this by, probably brought out the 1/6. So he probably has 1/6 times probably minus 16 e to the minus 2x plus 15 e to the minus x plus e to the x. Is that what the author's got? So this was 32. Not that we care what the grad student. Yeah, 1/6, 15 minus 16 e to the minus. Yeah. So that's exactly what he's got it in. He misspelled it. He put it in the wrong order. Okay. Let's do 38 next. 38. No, let's not. Let's do 48 next, because we're supposed to do a variation of parameter one yet. And you know you're going to have to do one on the test, so I better do one, right? So I got y double prime minus 2y prime minus 8y is equal to 3e to the minus 2x. In these problems, use the variational parameter to find a particular solution. So all we're doing is finding a particular solution. On the test, you're going to be told to find the answer using it. So you're still going to have to find the homogeneous solution. But we're just going to find a particular one. Okay, so I have a characteristic equation of the homogeneous solution, r squared minus 2r minus 8 is 0. and I can factor that r minus 4r plus 2 is 0, and I can find that r is equal to minus 2 and 4. And now I have y sub 1 is e to the minus 2x, and y sub 2 is e to the 4x. Okay. Then I need to find the Wronskian of y1, y2. Okay, so I'm going to have e to the minus 2x minus 2 e to the minus 2x, e to the 4x, 4e to the 4x, and I'm going to have 4 e to the 2x minus minus 2 e to the 4x, e to the 2x, e to the 2x. So I'm going to have 6 e to the 2x is my Wronskian. Okay, so 6e to the 2x is my Wronskian. My y1 and my y2 is that, and my forcing function is so my forcing function is 3e to the minus 2x. All right. So now I'm going to look on page 160. Y sub p is equal to minus y1 of x minus e to the minus 2x integral y2 is e to the y2 is e to the 4x. E to the 4x times the forcing function 3e to the minus 2x divided by the Wronskian, which is 6e to the 2x, plus the y2 e to the 4x integral e to the minus 2x e3 e to the minus 2x divided by the Wronskian 6e to the 2x. And I ran out of room for the dx's, but there still has to be a dx there, and there's still a dx over here, so I put them in. Okay, so I've got minus e to the minus 2x integral. All right, now I've got e to the minus 2x, e to the minus 2x, e to the 4x, they all go away. I got 1/2 dx plus e to the 4x integral. I got 1/2 e to the minus 6x dx. Okay, so I'm there. I got minus e to the minus 2x times 1/2 x minus e to the 4x 1/12 e to the minus 6x. Oh, I hope I did that right. All right. So I got minus 1/2 x e to the minus 2x minus 1/12 e to the minus 2x. Okay. Now, coming back up here, e to the minus 2x was part of the original thingy right there. So it doesn't need to be here too. It'll go away. So y sub p minus 1/2 x e to the minus 2x, and that's all there is. There ain't no more. See if the author thinks that way. 48. No, the author put in the minus minus 1/12. All right. So the author kept it that way. Let's see. Well, the author's right. That is correct. But when I write the final solution, y sub x, it looks like c1 e to the minus 2x plus c2 e to the 4x minus 1/2 x e to the minus 2x minus 1/12 e to the minus 2x, right? That's what it looks like. But this constant of integration, for lack of a better word, sucks up that one, that guy there. So you'd write it y sub p is equal to c1 e to the minus 2x, c2 e to the 4x, minus 1/2 x e to the minus 2x, because you wouldn't, that term wouldn't be there anymore. It would be part of the constant of integration. Go ahead, ask how I know to do that. Oh, I don't know. Must be some reason. All right. So I think we should do another one. Why don't we do 54? Let's see, yeah, we probably have enough time. 54. See, now if this were Thursday, I have a Buena Vista class starting at 5 o'clock, so we'd have to leave now. So your choice. Do I do 54 or do we leave now? Okay, 54. All right. Because it's got a cosecant in it. Who put that? What do you mean cosecant square? Anyway, so I got y double prime plus y is equal to cosecant squared x. All right, so I've got a characteristic equation. R squared plus 1 is 0. So R is going to be plus or minus I. So y1 is cosine x and y2 is sine x. Those are those guys. Okay, now I want the Wronskian of y1, y2. Okay, so cosine x minus sine x, sine x, cosine x, and that looks like 1. Cosine squared plus sine squared is 1. So the Wronskian is 1. What a deal. Okay, so y sub p is going to be equal to, looking at page 160 again, you don't do this without looking at that page, cosine x integral sine x cosecant squared x over 1 plus sine x integral cosine x cosecant squared x over 1. And again, I left off the dx's and the dx's. Well, I certainly hope that one of those is actually solvable, don't you? Okay, so y sub p cosine x integral. Hyperbolic cosine is not hyper. Cosecant is 1 over sine. So this is going to be 1 over sine x dx. And this is going to be one, this is 1 over sine. So this is integral of cosine x divided by sine squared x dx. Ew, that doesn't look good. All right, so I've got the cosine x integral cosecant x plus integral cotangent x cosecant x.
Is that a sine x integral?
Where?
The second one.
Here?
No, the second integral right before it, because it's supposed to be a sine.
Where? Oh, right here.
Yeah.
Yeah, that's so trivial to my problems. right now.
I know.
I have some real problems here, and you're making me look at something that's barely an issue, you know. All right, well, the integral of cosecant is easy enough to come up with. Where is it? Integral of cosecant. Okay, so this is going to be the cosine x times the natural log of the absolute value of the cosecant x minus cotangent x. Isn't that lovely? And then we're going to have plus the sine x times. Anybody know the integral of, oh, there it is. Look at number 11. Cosecant cotangent, I don't believe it, minus cosecant x. Oh, how simple was that? So this guy turns out to be number 11 in the front of book, and this guy turns out to be number 15 in the front of book. So anybody could do those integrals. I mean, how simple is that? You know. All right. So now y sub p cosine x natural log absolute value cosecant x minus cotangent x plus sine x. Now, the cosecant is 1 over sine, so this just becomes minus 1, right? Minus 1. Minus 1. Now, what makes us think that the author is going to have that answer? I don't know. So that's 54, 54, 50, 54. Minus 1. Okay, I got a minus 1. And I got everything right except I need a minus sign here. So let's go back up and figure out why there's no minus sign there. And right there is supposed to be, I was looking at it right there, page 160. There's a minus sign sitting right there, plain as day. Right there, plain as day. Right there. Right there. Right there. And now we agree with the author. All I would have had to do is bring a minus sign with me and life would have been so much better. Okay, good enough? Not too much weird there going on. Not too much. Okay.